Alright, so over the next hour, hour and a half, I'm going to be going over sets and maps, or more precisely, the data structure we use to build sets and maps, which are hash tables. Now, sets and maps are extremely powerful data structures. Learn about hash coding and to facilitate efficient insertion, removal, and search. When it's talking about efficient, it means efficient. A hash map and a hash set do their operations in constant time. Not log time, not linear time, constant time. Doesn't matter how big the hash table is, it will operate as efficiently as if it were 100 times smaller or 100 times larger. And we're going to be looking at also the different ways we implement hash tables to implement maps and sets. Specifically, we're going to be looking at implementing hash maps and hash sets. And we're going to look also about how to use them. I've already recorded the videos where I code up a map, a hash map using open addressing. So we'll take a look at that once you're done. But this half is more the theory and the using, and then the other half is the building. So we've learned about the list interface already, and that was a while back ago. But the big thing about lists is that they had indices. Things in a list came in order. For hash maps, we are going to be sacrificing any kind of semblance in order, and the same for hash sets. In sets, we don't have indices. We have no idea what order items came in to the set, but it's still efficient. So, for instance, I'll go ahead and just show you what I mean by what that second bullet point means. Does not review the order of insertion of items, right? So let's go ahead and create a new set of integers. Set equals new hash set. Okay. And set dot add 5. Set dot add 100. Set dot add 101. And now if we print out our set, we notice that our output is the set contains 100, 5, and 101. We put it in this order. And this is nothing. There is no order here. And this is because of the way the underlying data structure in a hash set works, which it has a magic magic way of figuring out where to put things in the underlying data structure. And it just puts them there, and then it can find them and retrieve it. All in constant time. Magic. You're going to hear me using that term a lot, even though we're going to peel back a bunch of the layers. But there is one thing that's going to mostly be magic, which is the hash function. We're going to go over how strings use the hash function, but it's mainly going to be magic because writing a good hash function is hard. It's like I did a dissertation on that or something. Well, touched on it in my dissertation at least. So, a set here is by the way, a mathematical set. So if you remember your union, your intersection, that's what we're talking about here. So maps do key value pairs. Actually, we use them for like 3 things, which is key value pairs, like associating an identifier like an email address with a value, such as that customer's shopping cart or your student ID with all the information about you. The second thing we do is for counting a bunch of things. So like if we want to count all the letters or all the words in a document and how much each one occurred. And then categorization, which is going through things and placing them into categories, where the key is the category and the value is the list of all the things that go into that category. So let's go ahead and talk about the set interface first. And then we'll talk about the maps and the map interfaces. So here, right, is the hierarchy. Okay, so we've got our set interface, and then we've got our hash set over here, which is where we're mainly focusing on. But it's just worthwhile to note that we have this thing over here called sorted set, which is an interface, and navigable set. It has this thing over here, which you might want to take a look at when you're done with this class. But the tree set over here, So you can implement a set using a hash map or a binary search tree. Now, if you do it with using a binary search tree, it takes log n time, but because it's a binary search tree, you're able to maintain order if you need things to be sorted. Hash set, though, says order schmorter. I want it in constant time. Right? So we've seen the set from our mathematics, right? Which is that a set is a collection of items that has no duplicates and at most one null. So if we go back to this, right, if I do set.add 5, it comes back false. And if I print it out, again, notice that there's no additional 5. So here, right, the add method, which has been returning true and true the entire time here, sometimes returns false. It returns false if there's a duplicate, which is useful. You can say, add this. Sorry, if adding this does not work, then I have a duplicate. This is especially useful if you're looking for duplicates in a list or something like that, because all it takes is O of n time now to go through a list. Add it to the set. Try to add it to the set. If you can't add it, you've seen it before. Do that for each item. And there's n items, and each of those is a constant time operation. Right, so what are the operations that we can do on sets? Membership, add elements, remove elements, and then do a union operation, the intersection operation, the difference operation, and the subset operation, which you obviously all remember, and so I'm not going to have to do a video about that at all.